The James Webb Space Telescope, or JWST, is widely recognized as the most advanced space observatory ever built, and it stands at the forefront of global space research. Its primary mission is nothing short of monumental: to unravel the mysteries of our solar system, probe the atmospheres of distant exoplanets orbiting alien stars, and study the vast cosmic structures that compose our universe. These efforts not only expand our understanding of the cosmos but also help us grasp our own place within it. In a groundbreaking initiative, scientists recently directed JWST toward a star located approximately 120 light-years away from Earth. What they uncovered was nothing short of astonishing. The telescope detected compelling evidence suggesting the presence of carbon-based molecules in the atmosphere of a potential ocean world far beyond our solar system, a finding that has electrified the astronomical community. But how was such a remarkable discovery possible, and what does it mean for our understanding of habitable worlds? This revelation offers a tantalizing glimpse into a planet vastly different from anything found within our solar neighborhood, while simultaneously raising profound questions about the possibility of life elsewhere in the universe. The exoplanet in question is K218b, a celestial body that is about 8.6 times more massive than Earth. What makes K218b especially intriguing is that it appears to possess a hydrogen-rich atmosphere and may be covered by a deep ocean beneath that gaseous envelope. Previous observations from NASA's Hubble Space Telescope had already hinted at something unusual in this system, but it is JWST's advanced infrared capabilities that allowed astronomers to detect methane and carbon dioxide in the planet's atmosphere with much greater clarity. These carbon compounds are of particular interest because they can be linked to biological processes, at least, as we know them on Earth. The detection of such molecules strengthens the theory that K218b might have conditions favorable for life. K218b orbits a cool dwarf star, K218, within the habitable zone, an area where temperatures could, in theory, allow liquid water to exist. Exoplanets like K218b fall into a rare category known as sub-Neptunes, planets that lie between Earth and Neptune in size. These are uncommon in our own solar system, which makes every discovery of such a world a valuable opportunity to learn more about planetary evolution and habitability. Because we lack nearby examples, studying distant sub-Neptunes helps bridge the gap in our planetary knowledge. One of the most fascinating aspects of this finding is the possible detection of dimethyl sulfide, DMS, a molecule that, on Earth, is almost exclusively produced by life, specifically by marine phytoplankton. If confirmed, it would represent the first time a biosignature gas has been identified in the atmosphere of an exoplanet. However, current evidence for DMS on K218b remains tentative and requires further verification through additional observations. While the presence of methane and carbon dioxide is encouraging, it is not, on its own, a confirmation of life. Several non-biological processes can also produce these gases. Still, the absence of ammonia, a compound typically expected in certain non-biological atmospheres, adds another layer of intrigue. The data so far suggest a unique atmospheric chemistry potentially shaped by processes we do not yet fully understand. It's also important to consider the planet's physical characteristics. With a radius approximately 2.6 times that of Earth, K218b likely has a core surrounded by a thick, high-pressure mantle of ice, much like Neptune. However, it also appears to possess a relatively thin, hydrogen-rich atmosphere and a potential surface ocean. Theoretical models suggest that this ocean, while possibly liquid, could be under extreme pressure and may not be conducive to life as we know it. Even so, the discovery of such conditions marks a significant step forward in the search for potentially habitable exoplanets. A major technical triumph of this research lies in how the JWST collected the data. K218b is a transiting exoplanet, meaning it passes in front of its host star from our point of view, causing a measurable dip in the star's brightness. During these transits, some of the star's light filters through the planet's atmosphere before reaching the telescope. JWST's instruments can then analyze the filtered light to determine the chemical composition of the atmosphere based on the absorption patterns left behind. This technique, spectroscopy, is one of JWST's most powerful tools. By examining how light interacts with molecules in a planet's atmosphere, scientists can identify the presence of various gases and even detect subtle changes over time. These measurements are helping to create the most detailed atmospheric profiles ever obtained for planets outside our solar system. The current research team plans to further investigate K218b using JWST's mid-infrared spectrometer to better understand its climate, chemical processes, and potential biosignatures. But JWST's contributions to astronomy don't stop at exoplanet exploration. In another stunning discovery, the telescope detected complex organic molecules, similar to smog or smoke, in a galaxy so distant that its light has taken over 12 billion years to reach us. These molecules, known as polycyclic aromatic hydrocarbons, PAHs, are made of carbon and hydrogen and are commonly found on Earth in fossil fuels and pollutants. That such molecules were already forming when the universe was only 10% of its current age is a major challenge to existing theories of chemical evolution. This discovery is both thrilling and puzzling. Until now, astronomers believed that complex molecules like PAHs required more time to form than the early universe might allow. Yet here they are, observed in a galaxy that existed just 1.5 billion years after the Big Bang. What makes this even more extraordinary is that the galaxy in question, SP4-1847, appears to have already formed stars that generated as much carbon and oxygen as those found in our Milky Way, a galaxy that is more than 10 times older. Such findings suggest that the universe was chemically maturing much faster than previously thought. With the JWST's incredible sensitivity, scientists can now not only confirm the presence of these molecules but also study their spatial distribution within distant galaxies. This opens a whole new frontier in understanding how early star systems and galactic structures evolved, and how they may have set the stage for life as we know it. These discoveries reflect a broader truth. The JWST is fundamentally changing how we see the cosmos. It's allowing us to peer deeper into space and further back in time than ever before. By studying exoplanets like K218b and galaxies from the universe's infancy, we are beginning to answer some of humanity's most profound questions. Are we alone in the universe? What conditions are necessary for life? How did everything we know come to be? Each observation brings us closer to answers, but also opens the door to new questions. The data being collected by JWST is not only confirming some theories, it's challenging others, forcing scientists to rethink what they thought they understood about planetary formation, chemical processes, and the timeline of life-friendly environments. Looking ahead, JWST will continue to play a vital role in NASA's search for habitable planets. Its unparalleled capability to analyze the atmospheres of distant worlds provides an unprecedented opportunity to detect biosignatures, trace complex chemistry, and explore the potential for alien life. Whether it's confirming the presence of dimethyl sulfide on K218b, finding new sub-Neptunes in distant systems, or studying the earliest galaxies, the telescope is poised to revolutionize space science for decades to come. Beyond its technical achievements, JWST represents something deeply human, our innate desire to explore, to understand, and to connect with the greater universe. It's a symbol of our collective curiosity and ingenuity. As we continue our journey into the unknown, the telescope will be our guide, helping us chart the story of the cosmos, one discovery at a time. With each passing year, the universe grows a little less mysterious, thanks to tools like JWST. And yet, the more we learn, the more we realize just how much remains hidden in the stars. From distant ocean worlds to ancient cosmic smoke signals, the secrets of the cosmos are out there, waiting to be discovered.